Hello, I'm Zhao from the University of Victoria. Today I'm really delighted to be presenting our work on interactive sonification for health and energy using ChucK and Unity. My supervisor in this project is Tzanetakis. In terms of the background, existing data sonifications can be limited in terms of being controlled by user in an interactive fashion. And interactions are important because they enable user to rapidly experiment with sound design and allow sonification to be modified in real time. When sonifications are interactive, they tend to be singular prototypes focused on one particular dataset. So we want to move towards an accessible interactive sonification framework, and one of the eventual goals from our project is to construct Tableau, but not just for visualization, but also for sonification. Details on related works of existing toolkits and sonifications related to health and energy are in our paper. In terms of our interactive sonification framework, it is built upon work on accessible sonification toolkit. It utilizes modern technology for audio and interface, and it can be used for any dataset in a tabular form in comparison to a domain-specific system. It also further supports the Compose sonification design space to distinguish between the continuous and discrete sonification. It also introduces novel methods to improve sonification experience, such as support for conditional discrete events, interleaved playback of multiple data streams for comparison, FM synthesis in terms of one data attribute modulating another, and synchronized interactive 2D and 3D visualizations. And these will be demonstrated with data in health and energy domains as case studies. Talking about the technology of our framework, we use ChucK, which is a programming language creating concurrent, strongly timed procedure audio. We also use Unity, which is a game engine creating a user interface and also specializing and visualizing the sonifications in our project. And lastly, Trinity, which is essentially combining both ChucK and Unity. In terms of the design of our framework, it is inspired by a typical digital audio workstation. As you can see at the top, we have some general controls that's responsible for data loading, audio playing, and mode selection. The track view is essentially horizontal rows stacked together, where each row is responsible for a data attribute. It also contains sound synthesis controls and parameter mappings, and at the bottom of each row, there is a visual plot of the data stream as a line graph. There is also a green cursor to signify the location of current data point being sonified. They are also randomly and differently colored for aesthetic reasons and also easy identification of attributes in the audio visualization view. Now coming to our case studies, we have selected two publicly available datasets in health and energy domains chosen from ICAD. The first one is EEG data, and the second one is about air quality. We have also successfully replicated the original certifications, and we have provided more details in our paper. Essentially, the EEG data is sonified with amplitude and frequency modulation, and the air quality data is sonified with FM synthesis. In each case studies, we also talk about how our sonification framework achieves more with interactivity and new functionalities appropriate to the context of the dataset. First, we have the EEG data, which was recorded under two conditions with the subject's eyes being open or closed. The alpha waves were then separated into low and high frequencies, resulting in 4 sets of data in total. So in our framework, we can see multiple data streams loaded together, eliminating the need to reload the data when the user wishes to focus on another dataset, especially when multiple datasets are related to each other in terms of their context. There are also easier real-time parameter controls for interactive exploration. So for example, the original paper uses pure data, and in a pure data patch, you might want to change your oscillators by removing the object and reloading another one. But in our framework, we can simply select another option in a drop-down menu. We also support conditional discrete events, which involve 2 parameters. Threshold means a certain value for the data to reach to produce a sound, and the increment is a value that could be added or subtracted to the threshold every time the threshold is reached. If not configured, then every data point is a discrete event. We also support the use of audio sample selection here, so not only can we utilize sound design synthesis, but also the user can customize their sound by loading audio samples. To demonstrate this, I have an example of the sonification of the EEG data for discrete events, with the threshold set for 2 and then changed to 5. And here I'm changing from 2 to 5 for the threshold. As you can hear, the pitch is higher, because only data values that are higher than 5 are being played right now. Next, we also support semi-automated envelope controls for the discrete sonifications, depending on the nature of sonification being discrete or continuous. For example, in this picture, this is the default automated value for a discrete sonification. If I toggle this back to continuous, then the sustain is going to be changed from 0 to 1 instead for a continuous sounding audio. Next, in our second case studies, we look at the air quality data, which was collected from the Canadian provincial websites. The data has SO2, O3, NO2, CO, and PM2.5 data, which were indicators of the air quality. In our example, we are omitting the PM2.5, which was used for granular synthesis, which is not supported in our framework. In our sonification of the air quality data, we're using FM synthesis not just for individual data attributes for their sound design, but also we can use it with one data attribute modulating another, which is not possible in the original paper. This means that oscillators, being either the modulator or the carrier, could be linked together without any restrictions and controlled interactively in real time by mapping any oscillator to another target oscillator, essentially creating different algorithms in FM synthesis. And this would allow the data attaching the modulator to influence the sound texture of the carrier, which could be attached to another data attribute. To demonstrate this, I have an example of CO data modulating the NO2 sound. This means that if the CO data gets higher, then the sound texture is going to sound more metallic. And if the data of NO2 is higher, then the pitch of the audio is higher. And here it sounds a little bit more metallic. And as CO data decreases, it sounds less metallic. And throughout the whole sonification, the pitch shifts depending on the value of NO2. Furthermore, we also support interleaved playback, which means selected attributes are sonified one by one to hear each data point individually, allowing for more exact and clearer comparison. And this kind of sonification is inherently discrete. For example, what we are hearing is 4 data attributes being sonified one by one, each after each. And this allows for a much clearer comparison instead of hearing everything at once. Lastly, we also support audio spatialization and also visualization with the power of Unity. The location of the speakers of the attributes can be dragged and moved to achieve an experiment with different audio pannings in real time. In this example, we're doing visualization and spatialization of audio for the 4 attributes which are mapped to distinct colors. These are also mapped to different audio pannings where the SO2 is on the far left and O3 on the far right. And here we can see the brown color is dominant, meaning the O3 values is the highest. And here we can see the gray and red color is getting more clustered, meaning their values are getting higher. And in both examples, we can see the green color is not very dominant, meaning the SO2 data has been low. As conclusion, we have succeeded in developing a sonification framework prototype that achieves various methods of sonification and visualization. It improves the sonification experience of 2 datasets related to health and energy, and it supports various novel functionalities. This is still a work in progress, and future work will include supporting for more expressiveness of the sound, real-time data input, being able to select the time scaling between data and playtime, being able to select regions of data to be played, and audio spatialization in 3 dimensions, and more comprehensive visualization. We also want to evaluate the user's sonification within the framework by designing some kind of task-based mechanism. Lastly, the framework itself should also be evaluated with a user study. Now, I would like to conclude my presentation and thank you everyone for your attention.